Okay, we've got a bit of a game today. I'm thinking of a complex number between 1 and 10, and it's going to be your job to guess it. Now, it's pretty hard with what we have on the board because there's an infinite number of different complex numbers of this form. So I'm going to need to give some hints. So to start with, forget about the 1 to 10 thing because that doesn't really make sense. But we'll start with the first hint now. Okay, so for clue number 1, we've got a minus 1 greater than b greater than 0. So everything for a and b is going to be positive. We also have this condition that we want a and b to be integers. We could just say a and b positive integers, but we've got this a minus 1 thing here. So what that's going to do, so for example, like 2 plus 8i, not valid because a is less than b. But we also can't have something, we want a greater than b, but we can't have something like 5 plus 4i because then we have consecutive terms. We've got that minus 1. So something that could work would be something like, let's say 6 plus 4i. So we want something like this, but that's still probably way too many things to guess from, right? Infinite number of possibilities. One thing I should say, just notation, when we have a and b integers in a complex number, those are called Gaussian integers. So we're looking for a Gaussian integer, something in this form here. And so I'll get rid of this and we can move on to clue number 2. Okay, number 2, z is not a Gaussian prime. Now that's interesting. We have some criteria on a Gaussian prime, which just says Gaussian prime means it can't be broken up into the multiplication of other Gaussian integers. We usually look at these in two cases. One is when one of the values is 0. So like we actually can assess this for just a real number 3, just looking at 3 as 3 plus 0i. And this would actually be a Gaussian prime as we can't break it up into smaller Gaussian integers. But the interesting thing is 5 is actually not prime because you can create 5 from, I'm not following this rule right here, but you can create a 5 like just doing 1 plus 2i times 1 minus 2i. If you multiply that out, that gives you a 5, but then we've broken it into a composite of two Gaussian integers. But we're not really interested in this case right here because we've already eliminated 0 with our clue number 1. So with neither value 0, what we want to look at is we want to look at the norm of z. And the definition for this is going to be just a squared plus b squared. And then for this, if the norm is prime, then z is going to be a Gaussian prime. And if it's not, then it's not going to be a Gaussian prime. So we know that this norm, this thing is going to not be prime. And when I say prime here, I mean not prime in the regular integers, not the Gaussian integers. Now from this clue, maybe we don't get too much because not a prime could come in a bunch of different forms. It's not necessarily odd or even or anything. One example we could look at would be like just something obvious, like let's say, and let me do something that's going to meet the first criteria. So if we did 6 plus 4i, this is obviously not prime as you can factor a 2 out of it. So you could factor it like 2 times 3 plus 2i, showing it's composite, where this is still a complex number. I mean, if you want, you could write this as like 2 plus 0i. So let's move on to clue number 3. Okay, so for clue number 3, it directly addresses what we just did. That example that I erased from the board, what did I have? 6 plus 4i. Because this is the case where we have like a trivial factorization where we factored out 2. And that's because the GCD, that's not 1, right? The GCD of 6 and 4 is just equal to 2. So with this condition, we've actually eliminated any case where both a and b are even, because anything like 2 plus 38i, any complex number where a and b are even, the GCD is going to be at least 2, so it's going to violate this. But you could still have something like 7 plus 3i. Both are odd. GCD is 1. And this is actually not a Gaussian prime. So as far as we know, this is still a valid possibility. It meets the first criteria, right? A is greater than b and all that. So we're starting to narrow it down, although there's still a ton of possibilities, but we're getting somewhere. So let's move on to clue number 4. Now for number 4, we want the norm to be odd, which is going to eliminate this one right here if this is our z value. But if we calculate the norm of this right here, this is going to be 7 squared plus 3 squared. That's going to be 49 plus 9, 58, which is even. So it's going to violate this. But that's going to happen whenever a and b are both odd. So from all this, we can put together that we can't have a and b both even. We can't have A and B both odd. And so what we're going to need to make this work so far is we're going to need one of A and B to be odd and the other one's going to be even. So we put that together with all this here. Let's move on to clue number 5. Okay, now for this one, it's not going to eliminate that many possibilities, but there are some obvious ones because if the norm is not a perfect square, that eliminates the Pythagorean triples. Like you're familiar, I don't want to do 3, 4, 5 as we have this condition, but if we had 4 plus 3i, and sorry, this one, and of course this isn't going to work because it's consecutive, but let's just do this anyway. So the norm of this, 4 plus 3i, 4 squared plus 3 squared, is going to be equal to 25, which is 5 squared. So if we didn't have this condition, there'd be a bunch of Pythagorean triples that you could guess. You notice it meets the other criteria, I think, right? GCD is 1, it's odd. So everything else is looking good, but this eliminates this kind of case. Probably the one, no, of course, like I said, this wasn't valid. So we could look at 5 and 12, again, trying to put it in the right order. So if we had the norm of 12 plus 5i, this is going to be 12 squared plus 5 squared, and that's going to be equal to 13 squared. So again, I think this meets all the criteria, right? Not consecutive, A is greater than B, GCD is 1, 13 squared is 169, that's odd. But we have to throw it out because of this criteria here, and that would include any of those Pythagorean triples. For Pythagorean triples, you can actually get to them with a formula. So it eliminates that whole strategy of just producing triples that might work. Okay, now with clue number 6, we're really starting to get somewhere because we've eliminated a lot of things. But what you might notice is there's still a lot of possibilities before clue number 6 where you can create a norm that's divisible by 5. If it's divisible by 5, unless it's 5 exactly, 5's a prime, but all those, 15, 35, 60, all those numbers are going to be composite, not a Gaussian prime. So there's a lot of candidates there that we're eliminating with clue number 6 here. An example of this would be, how about something like 8 plus I? If you look at the norm of this, it's going to be 8 squared plus 1 squared equals 65. These are really easy to construct because if, let's say you have A, we'll say A is going to be equal to plus or minus 2 mod 5. And then we'll make our B, and you can switch these either way, we'll make our B congruent to plus or minus 1 mod 5. Well, when you square A, it's always going to give 4 mod 5. When you square B, it's always going to give 1 mod 5. You add them together, you just constructed something 5 mod 5, which is really going to be 0 mod 5, which means it's divisible by 5. So you'd have a lot of these possibilities, but we just eliminate all of them just like this. And I think we're getting pretty close to being able to guess, but let me give you one more clue at least to see if we can solve this. So clue number 7 over here, what we want is, there's still multiple possibilities. There's probably still an infinite number of possibilities, I'm not sure. So in order to narrow it down, we want the smallest, we want to minimize the norm, a squared plus b squared. And I also give this hint, a squared plus b squared is going to be less than 500. So then now we're looking at just kind of a small group of numbers. I don't know how many there are actually less than 500. I'll tell you there's more than one answer less than 500, but at this point there's not that many. I will give one example that's not the solution, but that meets all the criteria. So let's take a look at that. So let's look at a complex number 18 plus 13i. So for this one, okay, criteria 1, we're good. It's not consecutive, positive integers. This is not prime because let's calculate the norm. That's going to be, let's do the calculating this norm. We just need to square everything. So 18 squared is 324, 13 squared is 169. Putting this together, this is going to be 493. We'll go through our list and check everything. The GCD of 18 and 13 is going to be 1 because 13 is prime. Now 493, you might not know, I wouldn't know without checking it, but 493 is prime. So it's going to meet this criteria here. The norm is odd, 493 is odd, that's good. 493 is not a perfect square and it's not divisible by 5. 493 is less than 500. Sorry, I misspoke a second ago. 493 is not prime, because if it was prime, it would violate 2 here. So 493 is actually 17 times 29. So this right here works. So this is a potential solution. It meets every criteria. The only thing is I can tell you there is a smaller number. It's not the minimum. So I guess it doesn't meet every criteria. It just doesn't meet this number 7 right here. So when I was going through it the first time, even though I created the problem, I was still basically just guessing, because then, okay, how do we find a smaller one than this without just like trial and error? Well, it turns out there is a systematic way to do this. Given everything we have here, what we can do is we know our norm is going to be composite. I mean, technically there's cases where, like, say the norm is 0 or whatever, or 1, right? Because 1's not prime or that kind of case. But we're not worried about any of that because we have this condition here where this is going to always be positive. So we're not worried about any kind of like negative non-primes or anything like that. So with what we have here, we're only interested in composite norms. So if we just call the norm n, we can write it, maybe to start, without making it too complicated, if it's composite, it's going to be made up of 2 primes, at least 2 primes, but we'll kind of consider that it's only 2 because we're trying to minimize. So we can come back and think about 3 or 4 primes, but it's going to be a pretty small list in order to minimize this with number 7. So we can look at this case by case. Just there's only a few different ways to look at this. We could set P1 equal to 2. So we could say our norm is 2 times some other prime. But right off the bat, this case isn't going to work because it violates number 4, that we want the norm to be odd. If we're multiplying it by 2, it's always going to be even. So we don't want any 2's in this. We really want P1 and P2 to be odd primes, and we'll only consider those. Next, we can look at the case, just naturally going up from 2, we can look at what if our norm is something like this. Well, this has a problem as well. The way we define the norm, or the way it is defined, is a squared plus b squared. So we have the sum of 2 squares. A and b are integers. We said they're not 0. What happens is, with the 2 square theorem, you never get integers in the prime factorization mod 3 mod 4 with an odd exponent like this. And so this would go for 7 as well, 11, 19. You can't have any of that with an odd exponent. So we can't have this case with the sum of 2 squares. What we could consider, though, is maybe something like this. So if that were the case, we want to minimize it. So let's pick like a small example. Let's say the norm is 3 squared, or 9, times 5. And so we want 45. But now that we've written it this way, and we're remembering that this is the sum of 2 squares, what you could do is reconstruct this. So like, to express 45 as the sum of 2 squares, the way you would do this is you would use the prime factorization. There's not really a good way to break up, again, the 3 mod 4 terms. So the way you would do it, you could write, for the 9, you could express it this way as a sum of 2 squares using 0. And then for 5, you could write it like 2 squared plus 1 squared. And then going backwards this way, you can actually turn this into a complex number. So like, all you do for like 2 squared plus 1 squared, I can write this as like 2 plus I. This won't always work. Sometimes it's going to be the conjugate, but this is kind of like the backwards factoring really quick. Turning the sum of 2 squares into 2 squared plus 1 squared, then writing it like this. Then this, I'd write it as 3 squared plus 0i. But that's really nothing, right? This is just a 9. So this is the same thing as 9 times 2 plus I. If we get it all the way back, we just have a single complex number here. I multiply that in, or I could leave it out just to show, either way, 18 plus 9i, but now it violates rule number 3. The GCD of this isn't 1, it's 9. So we can't have any of these kind of trivial factorings where we just factor out a constant. That's always going to happen whenever we involve anything 3 mod 4. So we have to eliminate anything like that and only consider values like 5 that are 1 mod 4. So constructing our norm out of primes that are 1 mod 4, we could try 5 and 13. Of course, that right away violates rule number 6 here. We can't involve a 5 because then we create a norm that's divisible by 5. We go to 29, which is 1 mod 4. We go to 17. We're trying to minimize it, right? So we don't want to go, we want to try to see if we can get something small what if we just tried, we can't have 5 and there's nothing else, so 13 is the lowest prime we can use. So the lowest possible number we could get would be 13 times 13, 13 squared, 169. But we can't use a perfect square. That violates rule number 5. 169, that's out, but we're getting really close. So what we can do, and I think you can see we don't want 3 primes. I mean, I don't know, I think that's kind of obvious, right? Because we're just going to create larger numbers. So, I mean, you could have like 13 times 17 times 29, but that's just going to be something bigger. So I think the smallest possibility we have is 13 times 17. Those are going to be, to get distinct primes, 1 mod 4, lowest two ones, not using 5, is going to be 13 times 17. You multiply that out, you get 221. Then doing that reverse factorization I mentioned before, expressing this as 2 squares, we just take 13 and 17 and write those as the sum of 2 squares. So for like 13, the way to do it, so this is going to be the same thing as 3 squared plus 2 squared. 9 plus 4 is 13. And then for 17, I can write that like 4 squared plus 1 squared. Also, a part of sum of 2 squares is that you can only express these numbers one way for a prime. So we only have one way to do this. But we don't want it broken up this way. We just want the single complex number, a plus bi. So we want to get, how do we express 221 as the sum of 2 squares? So we multiply this out using the identity for this. We just basically distribute, I'll show it out really quick. I did do this in another video, so it is kind of a crazy identity, but we're just gonna kind of distribute, I'll show it. So we'll do 3 times 4 is 12, plus 2 times 1 is 2. And then we multiply it the other way. We're gonna have 3 times 1, 4 times 2, so we're gonna have 8. When this one we change the sign, 8 minus 3, like this. We wanna add these. But then here this is 14 squared, which is 196. And here it's 5 squared, which is 25. Put that together, it's 221. Now that's one way to express it. The other way is just change the sign. So we have 12 minus 2 squared plus 8 plus 3 squared. This comes out to 10 squared plus 11 squared is still 221. So let me take these two factorings and turn it into a complex number. So for like 14 squared plus 5 squared, I can write this as 14 plus 5i. And then for this one, 10 squared plus 11 squared, we want a greater than b, so I'll reverse it and write it as 11 plus 10i. The norm again on both these is going to be 221. So now with all that, we have it down to just 2 candidates. Looking through, does it meet all the criteria? Yes, we have GCD is 1. They're both, again, that's not prime. We have the norm is odd, 221. It's not a perfect square. It's not divisible by 5. We have the a is greater than b in both these. The only trouble is we said with this, we can't have consecutive a and b. So what happens is this one, consecutive integers, this one goes away. So putting it all together, the complex number that I was thinking of the whole time was 14 plus 5i, and that's it. So there you go. Hopefully you were able to guess it within the first 2 or 3 clues. No, I don't know if that's possible. I guess if you were psychic, you got it. I mean, if you were psychic though, you already knew it from the thumbnail. I think there was plenty of information right there, just given a plus bi. But if you weren't psychic, I think you needed all the information up to the end. I mean, maybe once you got to 7, you could figure it out pretty quick, because then you have all the information you need. So, okay, that's it for today. Thanks everyone for watching. Have a good day.